Root of the inverse will be a one question on the multiple choice question on the AP test, most likely multiple choice. But again, we learn it because it's going to be easy if we get it down. It's super easy. So, all right, let's look at this then. Related rates. Our day 3 here, we're going to look at some more complicated situations. So, situation 1. All right, here we go. We're going to talk about a 16-foot ladder leans against a wall.
Did anybody ever you remember the problems you throw up on the board that all resulted in like Miss Copeland dying? And we would have to find like the length of like a wall she fell off of or something?
The bottom of the ladder, I think it's a little too dark.
Malevolent Michael.
The bottom of the ladder is 5 feet from the wall. At time t equals 0. Okay, and slides away from the wall at a rate of 3 feet per second. So it slides away from the wall at a rate of 3 feet per second. Find the velocity of the top of the ladder at time t equals 1. Okay. So there's our situation. All right, a 16-foot ladder leans against the wall. The bottom of the ladder is 5 feet from the wall at time t equals 0, and slides away from the wall at a rate of 3 feet per second. Find the velocity of the top of the ladder at time t equals 1. So you'll notice here there's no area formula, there's no volume formula given for this, right? We're not trying to find like the volume of something here, or we're not trying to find like the surface area. So, all right, there's no like formula given to us here, so we're going to have to like come up with that based on the situation. So what I'd like you guys to do right now is draw a picture of this situation. All right, draw the picture. Draw a picture. Okay. Yes, draw the time at t equals 0, I would say. So draw a representation of this, please. Okay, so actually draw a representation of
labels to these labels. Any more than just that's the ladder, that's the wall. Any number labels. Ladder, wall, round.
Like from your dress?
No, I just walked back and I saw it there. So I figured I'd
Oh,
yeah, got it.
Way to save the
Kyoto. That's right.
So wait, should you get that side to be like that?
Yeah, I mean, that's true. Yes, you
should, because otherwise we'd be kind of stuck. But yes, exactly. Okay. So I saw a lot of this. So let's see here. So we're going to like draw. There's our wall. Okay. There's the ground. All right. And then there's our ladder. And some people just didn't bother actually drawing a ladder, which is fine. I'm going to draw a little ladder. Happy little ladder.
what's the definition of friction of the ladder against the wall?
Right, exactly. We don't have to
We're
worry
gonna
about
need to know.
that. No. Friction coefficients or anything like that. No. Okay. Ladder is 16 feet. Okay. We're going to start, and what we're going to assume, and Donovan asked, and he's correct, so we can assume that the wall and the ground make what kind of angle? A 90-degree angle. All right, and let's see here. We have then the ladder starts at time t equals 0. The ladder is 5 feet. And then at time t equals 1, slides away from the wall, find the velocity of the top of the ladder at time t equals 1. Oh, we don't know the time. We don't know how far away it is at t equals 1.
Wait.
Well, it's sliding away from the wall right at 3 feet per second, and so if we start at time t equals 0, it's 5 feet from the wall. 1 second later, how many feet would it be from the wall? 8 feet from the wall. Ah, okay, so there's a piece of information that we... Huh? Never mind? Okay. So now we want to find the rate of change, or I should say, sorry, find the velocity of the top of the ladder. So here's the top of the ladder. What's going to happen to the top of the ladder? Yeah, it's going to go down, right? Okay, so we want to find kind of like the rate at which the top of the ladder is going down.
So could we could use the angles?
Well, the only angle,
so what we could do is we could do another mock-up of the ladder 8 feet from the wall, and then
okay.
So and then use it's like the special rate triangle formulas to find the length.
Yes.
The length,
right?
And then you find the difference between the height of the ladder against the wall at 5 feet, and then the height of the ladder against the wall at 8 feet.
And then do the difference.
Yeah.
Average change. Shh. Okay, so guys, I'm not going to talk over you, so I need you to listen here. Okay. Thank you. All right. So the special right triangles wouldn't work in this situation. We don't know it's a 30, 60, 90 or a 45, 45, 90. Not necessarily. Now, granted, I guess if this is 8 and that's 16, then that would end up being a 30, 60, 90. But that's not what we're talking about here. And we don't really know. I mean, we could find an angle here, but we don't know like the rate of change of the angles. We're trying to find derivatives and stuff like that. The relationship we want to use here, if you look, we have a length of a side, we have a length of a side, and then we have another side right here. We have what kind of shape do we have right here? See, and what kind of triangle? A right triangle. Okay, so what can we use to relate all three sides of a right triangle? Pythagorean theorem. So the formula we're going to be using here is a squared plus b squared, right, equals c squared. Now, I don't want to use a and b and c here. I'm going to change up the variables just slightly. So for this horizontal distance, let's call that x, because x normally represents like a, if we talk about x, we're talking about horizontal stuff. And then a vertical distance, let's call that y. And then that makes this diagonal here. Well, what are we going to call that? I'm just going to stick with the C, I think. I'm going to stick with the C, just because. So rather than a squared plus b squared equals c squared, let's call it x squared plus y squared equals c squared. Okay.
Shouldn't you, for C, can you just make it 15 squared? It doesn't change.
We'll talk about that. Yeah, we'll talk about that. But yes, in a sense. But yeah. We'll talk about that in a second here. So, x squared. So, all right. So let's see here. So we've got a formula. So now we can take the derivative of that, right? Because we want to come up with the rate of change, right? Well, actually, before we do that, let me, figure out here. We're trying to find the velocity of the top of the ladder. I feel like I should go this way instead. Sorry. So we want to find the velocity of the top of the ladder. So is that y that we're trying to solve for here? Velocity is a rate of change, right? Velocity is the rate of change of the top of the ladder. And so how do we denote the rate of change of the top of the ladder?
Position 1 minus position 2 over time. Position over time, right? Position over...
Okay. Well, we want to find it's not average velocity, so we want to find that probably means that it's instantaneous velocity. If it doesn't say average, we assume it's instantaneous. So how will we denote that here? Oh, well, okay, feet per second would be the units. I'm talking more like the calculus, like, symbols. Yeah, y prime or dy dt. That's what I was looking for. Maybe I didn't ask the question very well there. But the idea is we are trying to solve for, we want to solve for dy dt. That is the question here. Okay, so again, notice that took a little bit of interpretation, right? We were not told explicitly, find dy dt. All right? We weren't even really told to find the rate of change of the height of the ladder. We were asked to find the velocity. So that took a little bit of interpretation on our part, and not like guessing interpretation. That took us knowing that velocity means rate of change. That took us knowing that, okay, it's this vertical, length here, which we called y was the length, but then the rate of change of that is dy dt. So that's what we're solving for there is dy dt. All right, let's see. Do we know any other pieces? I told you, we figured out that at time t equals 0, x is 5 feet. At time t equals 1, x is 8 feet. What can we say dx dt is? What's the rate of change of x? Do we know that? Yeah, Connor? So, 3 feet per second, and slides away from the wall at a rate of 3 feet per second. So this dx dt is 3 feet per second. So there's another value that we know there. We're going this direction, 3 feet per second. Okay. So I think that takes care of all the values we know, right? We have a 16-foot ladder, that's labeled right there. That's C. The bottom of the ladder is 5 feet from the wall at time t equals 0, slides away from the wall at a rate of 3 feet per second, so dx dt is 3 feet per second. Find the velocity at the top of the ladder at time t equals 1. So again, the velocity at the top of the ladder, that's dy dt. And so there's our formula that relates all those things, the Pythagorean theorem. So now we have all of our kind of values, including the one we're trying to find. We want to find that dy dt. So now what can we do with this? Take the derivative, right? That's the next step. Step 1, get all your known piece of information, draw a picture. Step 2, get a formula that relates those things. And then 3 is when we take the derivative with respect to t. So derivative of x squared with respect to t, 2x dx dt, plus derivative of y squared with respect to t, 2y dy dt. And then derivative of c squared with respect to t, 2c dc dt. Yeah, it's a lot of rhyming kind of stuff. dc dt, dd dt, 2c dc dt, yeah. Okay. So let's start now kind of plugging in. All right? We want to find the velocity at the top of the ladder at time t equals 1. So what's the x that we're going to plug in?
X is 5.
So, yeah, is it the 5 or is it the 8? Why is it 8? At time t equals 1. Yeah, that's the key there. Time t equals 1. So it's going to be 2 times 8. What's dx dt? 3. Right? We were told that. Plus 2 times... Ooh, what's y?
Original Pythagorean theorem to find.
Right, so we have to solve for y here. We are not told what y is. We have to do a little side work over here. We're going to redraw that right triangle. Y is this side. What's this other leg going to be? 5 or 8?
8 because, yeah.
At time t equals 1, we want to use the leg length of 8. And then this hypotenuse is 16. Okay, so it's going to be y squared plus, oh, and I'm getting off the screen there a little bit. Let me zoom out a skosh. Okay, y squared plus 8 squared equals 16 squared, so y squared plus 64 equals 256.
Yeah.
Y squared equals... Okay, so it's the square root of 192 it looks like. Or sorry, it's 192 when you subtract, and then it's y equals the square root of 192.
Which is...
You want to leave it as that?
I would suggest leaving it as that. I would really recommend, guys, whenever you can, to wait to round until the very end. Wait to round until the very, very end. Intermediate rounding can result in, rounding in between steps instead of at the very end can result in, imprecision, and we can potentially lose points if we get off by a decimal place. So square root of 192 is our y. And then dy dt, that's what we're solving for, equals, and then 2c is 16, and then what's dc dt? We're not told here what the rate of change of the ladder is. What's that?
The
It doesn't change. What do you mean it doesn't change? The ladder's always going to be 16. So what would dc/dt then have to be? 0, because it does not change. It's constant, right? The rate of change is 0. It's not. If we put a 1, that means it's increasing. So yeah, it's just 0. So that means this equals 0.
Could we have just written it as a constant?
If you wanted to, and then taking the derivative, yeah, initially. But I would prefer doing it this way because I always hesitate to have you guys plug in stuff before you take the derivative. So that's why I want to do it that way. All right. So is everyone clear about where all this information came from? That is a packed little piece of, a little equation right there. So is everyone okay with everything where that came from? All those pieces?
The 0 came from the rate of change of
The length of the ladder. The ladder is
ladder's always 16.
it's always 16, so it's not going to shrink or get longer. So it's 0 is the rate of change.
If it was 1, it would be like 17 at T1.
Like, yeah, if the ladder was like somehow changing its length as it was falling, which doesn't really make sense, right? So it has to be a 0 rate of change. Ladder's held constant. Okay, unless it was like one of those, those like extending ladders and like the locks weren't in place and it's just like, yeah. So that could work. But anyway, so here we go. So now we're just going to solve this. So 2 times 8 is 16, times 3 is 48, plus 2 times the square root of 192 equals dy over dt. Subtract the 48 from both sides. So dy dt equals negative 48, and then divide it by the 2 square roots of 192. So it's negative 48 over 2 square root of 192. Again, if this were a free response question, and by the way, these related rate problems really lend themselves, really, make for good free response questions. Okay, and so now if we were, so you could stop right there. Okay, we could stop actually right there if we wanted to. We don't need to simplify that. And we could say, what would the units have to be here, though? Feet per second. We're talking about sliding down the wall there, so it's going to be feet per second. It's also a velocity, right? That's the normal kind of units for velocity. Okay, or if you wanted to as a decimal. Okay, if we want to type this in a decimal, we type in negative 48 divided by 2 square root of 192 and hit enter, and so our answer is negative 332.554.
Yeah, something's wrong about that.
No, Mr. Widmeyer.
You know how much these are out?
There should be 5. Should be. Wait, what do you mean I'm wrong?
You're wrong.
You're wrong.
What'd I do wrong?
You put the 2 root 192.
The denominator needs to have parentheses around it, because right now all that the calculator is going to divide is negative 48 divided by 2, and then multiply that answer times the square root of 192.
Could have just simplified it to negative 24 over root 192.
Whoops. So it should be really, negative 1.732. Remember, calculus commandment, how many decimal places do we round to? 3. Okay. And correct units. So that's an acceptable answer as well. And you can round or truncate. In this case, it's the same answer. So, all right. Questions on any of that? This is our first. This is kind of strange. This is kind of strange here. We ended up with a dy dt that is negative. We never really ended up with rates that are negative. Why is our rate negative here? Because the ladder is going down. That's right, okay? So the dy dt, it's a negative rate of change. Remember, velocity or derivatives, they have like a directional kind of component to it, right? If it's negative, it's like going down or getting smaller or whatever that might be. And then if it's positive, it's going to get bigger or longer or whatever it might be. Okay? So that's the answer. All right, let's try another one. Different situation. And I think, actually, how many do I have here? So we're doing 3 totals. This is the second of 3, and the third one looks like it's going to be pretty straightforward. But oh well. Okay. Water pours into a conical tank of height 10 feet and radius 4 feet.
guessing this is at the top, like the wide end of the cone.
Yes, it is it's like a ice cream cone looking, that orientation.
Yeah.
Okay, and, pours into a conical tank. Oh, okay, and so water pours into a conical tank of height 10 feet and radius 4 feet at a rate, so like the water's pouring in at a rate of 10 cubic feet per minute. Okay. How fast is the water level rising? Yep. How fast is the How fast is the water level rising when it is 5 feet high?
The cone, it would be like going really fast and it gets slower.
Right, exactly, because it expands out and it takes more to fill it up that fast. So, how fast is the water level rising when it is 5 feet high?
You know, we should find the acceleration of the water. Go higher fast.
Water acceleration. Alright, so we'll draw a picture here. And so, like I said, it's like an ice cream cone, right? Upside down conical tank. It would be kind of hard to pour into a cone that was like, you know, sitting on its base, I guess. It wouldn't quite be a cone. Alright. Yeah, I don't know. Yeah, it'd be something funny. And so let's see, we got our cone, and so let's see, we want to label some things. Water pours into a conical tank, height of 10 feet. Aha! So the full height is 10 feet. Okay, that's the height. 10 feet. Or if you want to, you can measure it from, like, bless you, from like the center there. Okay, that height there is 10 feet. The radius of the tank, the full tank, right, so the entire tank, is a radius of 4 feet. So you can go this way. And so this right here is 4 feet. That's R. It's 4 feet. Okay. Well, the problem is, right, the water, is it going to have a depth of 10 feet or a radius of 4 feet? No, that water is going to be, it's constantly being pumped in here, so it's going to be, you know, at some, like, level, so let's just, like, there's the water level. Okay, because we're trying to find how fast is the water level rising when it is 5 feet high. So, like, the water level in our situation is going to be 5 feet. And the last thing is the water is flowing in, okay, at a rate of 10 feet cubed per minute. So that's like dV dt, 10 feet cubed per minute, right? That's the rate of change of volume, 10 cubic feet per minute. Exactly. It's kind of like a giant water cooler pouring water cooler into a giant one of those paper cups. It's a giant water cooler. It's like a water cooler for giants, basically. This is like if giants ever come in and invade our country, then we'll know what to do. Build them giant water coolers and be like, oh, do you want to know what the velocity is? How fast the velocity of the water? And the giant's like, no, smash!
Do you want to know how fast?
And make us jelly. Okay, so ideas here. What's the formula that we should maybe try to use to relate all this stuff?
Well, we need maybe the volume of the cone.
Yes, volume of the cone, right? Water, right, as a liquid, and I guess as a gas. It takes the form of the shape that it's poured into, right? So, in this case, we're going to be forming a cone with the water when it gets poured into the tank there. So, we're going to use the volume formula for a cone. Volume equals 1/3 pi r squared h. Now, we've got a problem here, though, and that we have R and H. We want to get this, again, generally when we take the derivatives, we want to have it all in terms of like one variable. Now, I guess that kind of was like not true in number 2 right here, right? We did kind of be able to get that in terms of one thing. But here's the thing. If I were to take the derivative as this is written, I would have to use the product rule. And it would require me to, I would eventually have to take the derivative of R, and I'd eventually also take the derivative of H. All right? So, do I know anything about dr dt, the rate of change of the radius? I don't. Do I know anything about dh dt? I don't. But, what's the thing I'm trying to find? dh dt. So, this equation, do I want to get this? So, I can't solve it as it's currently written. Right now, it's got r's and h's in there. And if I take the derivative of this thing, like dv dt, we've got that. R, we've got radiuses in here. We've got some heights, too. But we don't have dr dt. We know nothing about dr dt. So, I have a problem. If I take the derivative as this is currently written, I'm going to end up with a dr dt. And I won't be able to solve that because we don't have any information about the dr dt. But I am trying to solve for dh dt. So, I'm going to rewrite this equation in terms of one variable. Well, what variable had I better use? I want this all to be in terms of h. If I leave it if I make this in terms of r, I'm going to end up with dr dt, and I don't know any dr dt's. If I put this all in terms of h, I'll end up with dh dt's, which is what I'm trying to solve for. So that's why we want to rewrite this thing in terms of h. All right, we want to rewrite this thing in terms of h. Okay, how are we going to do that? Because we are not told anywhere in here any sort of relationship between r and h. Sometimes we give a relationship. Sometimes we'll be told, oh, the radius is always twice the height. But we're not given any sort of relationship here. But we have what kind of shape right here? We have a triangle, and it's a right triangle. And then what kind of shape is this? Also a right triangle. And these two triangles, how are these two triangles going to be related? They're in the same angles, and so therefore they are going to be similar. So not congruent, they're similar. That means their sides will be in the same proportion. What theorem is that? Angle. Similarity theorem, because we have the same angle shared here, and then they both have right angles as well. So it's angle similarity. Okay? So what that means is that this unknown height here, I guess we know it's a height of 5, this little height here of my water and the little radius of my water is going to be similar to similar in proportion to the height of my tank and the radius of my tank. And we know the height of the tank and the radius of the tank. So what that means is I can take, for example, the radius of my water over the height of my water, and that's going to be in the same proportion as the radius of my tank, 4, over the height of my tank, 10.
Wait, the height of the water? Isn't the height of the water just like 5?
At an instant, it's going to be 5, but generally speaking, it's going to change, right? Same thing with the radius, so that's why I just wanted to use the general kind of information here. Okay, so with that being said here, then now again, the whole goal is here is to rewrite this all in terms of h. So that means what variable should I solve this for? If I solve for h, I'm going to plug in for h, and it's going to give me all r's.
Solve for r.
Yeah, we actually need to solve this for r. So r is equal to, I'm going to simplify that, 2/5 h. 2/5 h. All right, because I simplify 4/10 is 2/5. So now that I know that r is 2/5 h, I can take this volume before I go ahead and take that derivative and make it 1/3 pi, not r squared, but now what squared?
2/5 h.
Yeah, 2/5 h squared. This is one of the most difficult ones we could potentially see. Okay, is this kind of problem? This is the highest level I would say you guys need to worry about. So if you're not freaking out, but if you're oh, this is really complicated, you're right. It is. It is complicated. Okay. Yep.
Why don't we just plug in 5 either?
If we plug in the 5 right now, then my because the h is changed, I'm not sure. That might still work. I mean, we can examine that later. But
You're always going to be at 5. We're always we're just doing at 5 feet. So.
right, but then my problem is that if you guys are going to plug in 5 here, then you might plug in 5 here, and then you're going to now no longer have a DHD. You won't have, when you take the derivative, it'll just all be 0 because you've plugged numbers in. So that's why I'm hesitant to do that right now. I want to hold off on that. We can plug in the 5 later when the h shows up, but right now I want to hold off on doing any sort of that simplification because I don't want to lose anything. So let's simplify this. 1/3 pi, let's see, 2/5 squared, 4/25. H squared is h squared times h. And so I can finally write then, let's see here, I guess I can simplify these fractions, can't I? 1/3 times 4/25 is 4/75 pi. And then h squared times h is h cubed. Whew. Easy. Ooh, so all that work, and now we've got finally v in terms of h. And so now, what's our next step? Derivative. Okay, now we can finally take that derivative. dv dt equals. These are just coefficients here, right? 4/75 pi is a coefficient, so we can bring that 3 out front. The 3, well, I'm going to just go ahead and do 3 times 4/75. I'm not going to try and do too much simplification at once here. So the derivative of h cubed is 3 times the 4/75 pi h squared.
Which is 12/75.
Yeah, don't forget times dh dt. Sorry, that's what I wanted to make sure. And then yeah, we can simplify the 3 with the 75ths, can't we? 3 cancels out with the 75 to make it 25 there. And so I get dv dt equals 4/25 pi h squared dh dt. I'm running out of space, I'll have to go up to here. Alright, so again, I would say the trickiest part here was this simplification, right? This substitution right here, converting r in terms of h. Once we've done that, then it's just a matter of simplifying and taking the derivative, and we should all be comfortable with doing that derivative there, okay? And the simplification there too. It's just this substitution that makes it tricky. Because now we have the derivative, now what do we do? Plug in our known values, right? So what's dv dt? 10. Alright? Equals 4/25 pi. What's the h? Yeah, at the instant when the water is 5 feet high, so 5 squared, times, what's dh dt? That's what we're solving for. We're going to solve for dh dt. So actually this simplifies kind of nicely. 5 squared is 25, right? So it's 4/25 pi times 25 dh dt, and what does this result in then? Just 4 pi. So 10 is equal to 4 pi dh dt, and then to finish solving, what do we do? Yep, divide both sides by 4 pi. It's 10 over the quantity 4 pi. So we type that into my calculator here. Okay. Again, you can stop there. Actually, let's just say that. So we can stop there. What would our units be? dh dt. Bless you. Feet. So it's a height. So it would be cubed. A height is a linear measure, so it would just be feet per minute, or approximately, if we wanted to use the decimal here. Let's see here. 10 divided by 4 pi. So 7.854? No, Mr. Widmeyer. Cut it out, Mr. Wid. It's getting old. Put parentheses on your denominator, guys. 0.796 feet per minute. Okay. Oops, you can't see that. Yeah. Okay. You can see how significantly different those answers are if you don't type it in correctly. So please make sure you're typing things in correctly. Right? That would be so frustrating. All right, so let's review, since Tyler says he has no idea what happened in that problem. let's review. We have a conical tank, so I drew a cone. With a height of 10, so the full height's 10, the radius of that cone is 4. So from the center to the edge, 4. The water's pouring in at a rate of 10 cubic feet per minute. So, okay? How fast is the water level rising? That's H, right? Level of the water is the height. When it is 5 feet high. So we're asking the dH dt of the water when the water level H is 5. So I drew all that in there. Now, the water level at any time is going to be different, right? Earlier the height's going to be smaller. Later on, it's going to be like greater. Same thing with the radius too. The radius will be constantly changing. Okay, the lower the water is, the smaller the radius will be. The higher the water level is, the greater the radius will be. And so we need to come up with some sort of relationship here between all these things. Well, so this is the volume of a cone. So like that, you're like good with, right? The volume of a cone, 1/3 pi r squared h. The problem is, if we were to like just go straight from here and take the derivative, it'd be a product rule, which is like, yeah, it'd be a hassle. We can do the product rule, not a big deal. But the bigger problem is that when I would take the product rule here, I would end up like, you would agree I would end up with like dr dt and dH dt in there, right? Now, it's very clear here, the problem is asking how fast is the water level rising. So we want dH dt, that's what we're going to solve for. The problem is, though, if I take the derivative right now, I'm also going to have dr dt, and I don't have any information here about the rate of change of r. Nothing, and no way to kind of figure it out here either. All I know is the volume. So, what can I do? Well, instead of taking this formula as it's written, I can rewrite it using this similar triangle relationship here, okay? R, we want to eliminate that and rewrite it in terms of h. Well, as it turns out, this water level here is going to have a radius of r, a height of h. It will be in similar relationship to the radius of the full tank, 4, over the height of the full tank, 10. So r over h is going to have to be in the same proportion as 4 over 10. It's going to be constantly similar to itself. Okay? So then I was like, oh, okay, well there's a relationship. So that means r then is always 2/5 h. So instead of writing r, make it 2/5 h. Simplify, now it's all in terms of h. Now when I take the derivative, I only have dH dt, which is what I'm trying to solve for. I have h, which I know. I have dV dt, which I know. And so I know all the pieces I need to then be able to solve for dH dt. Go through it, okay? That's the idea. All right, any other questions on that one? Right, it's hard when you're like in the middle of the problem, but then once you get through it, you can like now go zoom out and see the big picture of it. It helps. Right. Well, I'll tell you this, that's like in a cone, in a conical tank kind of problem like this, you're going to use that similar triangle relationship. That's going to show up, okay?
Remember the other day when I said, I always am sitting in that, and I see a problem, I'm like, oh, this can't get any harder.
And then it does.
And then it magically gets harder.
Right, I just was laughing to myself when you said that.
Wonderful example.
Yeah, that's right, I just was laughing to myself when you said that. Okay, so I'm going to have you guys try one. So try a rectangular fish tank. Or rectangular prism fish tank, I guess I'll say. Because you really can't have a fish tank. That's right. If the fish fit in a rectangle, I don't know what kind of fish you're talking about there. All right, a rectangular fish tank, rectangular prism fish tank, is filled with water. At a rate of 3 feet cubed per minute. How fast is the water level rising if the base of the tank is a rectangle of dimension, I'm not sure if I see that plural or not, dimension 2 by 3 feet. There's a rectangle of dimension 2 by 3 feet. I think it's dimension 2 by 3. I don't know, actually. I'm not sure. I'll let you guys decide whether you want to put an S there or not. Okay. So how fast is the water level rising if the base of that tank is a rectangle of dimension 2 by 3 feet? Alright? So now I've changed the shape of the tank on you. It's not a conical tank, it is a rectangular prism. So again, you might want to draw a picture, might help. Okay. Don't forget to like label out all the things that you know and what you're trying to solve for. And then yeah, go from there.
Let me show you one other thing. So, what I'd like to do, maybe I'm like, I have this one that we got. Actually, we get a different color. Yes. Yes. Yeah. You want to run it? Okay.
Maria, we don't know one.
I'll be right back.
Which two you like? And so we get that. Equal to.
Yeah, no.
You're trying to find a derivative of the height.
It's
just
fine.
solving equation.
Well, it's all going to be the same. It's going to be changing at a constant rate for each
What's the
rectangle.
volume formula of
Yes. So I mean, it's
Or-
just
Well, base times width times height. You mean like
is
length times width times height?
Yeah, what?
Okay, it's base area times height if you want to do it that way too. Yeah. So question. Length times width times height.
so the volume of this rectangle is 6
The
each.
prism.
So the derivative of that would be
dv
Times-
dt equals
Volume of rectangle, 0.
dh dt. dv dt is 3. 6.
We're trying to find it. So DVDT is 33. I'm not sure.
I'm not sure if that's right. So.
0.5. Yep. So I'll say this: since, well, all right, well, I'll hold off on saying anything right now.
One half.
Yes.
Would DLDT and DWDT be 3 and 2 because they're always the same?
So, they, it's always the same. So that means what's the rate of change of it then?
So 0. So DLDT and DWDT is 0.
Yeah. So now be careful. If you take the derivative as you wrote that there, it's technically a product rule.
Yeah.
So, but here's the thing. What we can do though here is that since the length and the width never change, you can plug those in before you take the derivative. Because they're not changing. And in fact, you kind of have to because otherwise it's kind of tricky. Yeah, that's it. Yeah, no units. Well, so what did you find? It says DHDT. So what was the units for H2?
It's so like.
B and C would be, so B for.
Do that.
Yeah, you don't want to do the derivative split like that because you would have to take a product over like 3 things and it was kind of unhappy.
You know
So what we can say is that, like for example, the 3, is the water's width ever going to not be 3? Or the length, whatever it's not. Or its width ever not be 2? Yeah, so we can go ahead and plug the 3 and the 2 in right off the bat.
Yeah, I started plugging those in.
Sorry to hear that. Did you stick it out because you're like, I gotta stay for calculus? No, you don't do that. Well, thank you, I appreciate that.
And then, like, you just see what you have.
So, nice, derivative, yeah.
Height, rate for volume. It's just like, oh, volume, volume formula. And then just plug in, just don't take it, plug what you do have, take it really. You gotta figure this out. One half one. For the base of the, I think it's these for. Sure. They take a bit. Well, my brother forgot.
That's what I would do.
Is it? Okay.
Yeah. You should get one half. You can get one half. Feet per minute. Okay. Okay, cool. Let me get Mackenzie started real quick, and then I'll be...
I don't really big half.
So for example, if you see a box like
I gotta put the fan trying to
however, if you have a box like this, does not have a label, right? You can literally do it. I labeled it like this, so a girl, 5'9". So you take one of these, slap it across that, check the 5 to 9 boxes, and mark them, and just 8 around the edges so that it won't leave any. And then you can put a rubber, see if you can get a rubber band going around that. I got some there. And then just put it over.
Oh, yeah. Our entire Thanksgiving is probably last for a whole week. At that point, I get tired of eating turkey and
Okay, let's take a look now. How fast is the water level rising at the base of the tank is a rectangular dimension 2 by 3 feet. So, I'll say this is the 2 side, and that is the 3 side, and we've got water in the tank. Okay. And we got some water in the tank. Okay. Happy little water. Some ripples. Okay. And we don't know H. So we know the volume formula here is length times width times height. All right. For this, we know we're going to use volume because we are given the rate of change of the volume. We've got dV dt, so water's kind of like pouring in at 3 cubic feet per minute. Okay? We want to find how fast is the water level rising, so that means we want to solve for what? dH dt. So that means we need to get a dH dt here. Now, you'll notice if we were to take the derivative as this thing is currently written, what would we have to use? Product rule. And it'd be like the product rule applied like kind of twice here. It's kind of hard when you have 3 things being multiplied together. So we're going to skip that. We're going to skip that. Okay? Because we know that, for example, the width of the water, or I don't know, maybe we'll call this the length of width, whatever. This 3 feet, is that ever going to change? Is the water ever going to not be 3 feet in length or width? No. Right, unless like it's just initially filling up. But the idea is that this is different than that cone problem we did. In the cone problem, as the height increased, the radius of the water was constantly changing too. It was increasing as well. Here, this length and this width, they never change. So we may plug in those values to start out. And so we get that V equals 6H. All right, and now at this point, we have that relationship. We can take the derivative. So dV dt is equal to 6 dH dt. And so dV dt is 3, and that's equal to 6 dH dt. And so we divide both sides by 6, and we get dH dt is 1/2. And 1/2 what units? Feet per minute. Just feet. Again, because what are we measuring here? dH. H is a linear measure, so just feet, and then per time minute. Okay, so 1/2 feet per minute. 1/2 foot per minute. Half
How
foot.
is that because, like, length is in feet and width is in feet, so it'd be feet squared there.
Yeah. Yep.
When's the quiz on this?
I think the next assessment will actually be a test.
Oh,
Whoa!
Wait, did you hear my quiz?
No, I did not.
I'm ready for that.